So let's say you believe me that we can take polynomials or matrices or any old thing that has a addition-like operation and scalar multiplication-like operation, that we can treat those things like they're vectors and do linear algebra with them. If you believe me, then I still have to answer the question, how? How do we take a polynomial function and turn it into something that we can do linear algebra with? This process of taking away the context, taking some object which we're going to think of temporarily as being a vector and stripping away its unique characteristics and making it into a dry, boring vector that lets us use what we already know about linear algebra, that process is called finding a coordinate vector for our object. So in this video, we want to look at how we might find coordinate vectors for things like matrices and things like polynomial functions that we want to treat like vectors so we can do linear algebra with them, but which don't look like vectors when they first arrive on our doorstep. So what is that process? Let's start by taking a matrix like this one. We want to figure out how to transform it into a coordinate vector. So I've got kind of a blank coordinate vector over there for us to use. So what is going to be our tool for traveling back and forth between the world of context, where our matrices are really matrices, and the world of no context, where our matrices are just plain boring old vectors that we nevertheless know how to do linear algebra with? That tool is a basis for our vector space. So if you tell me what is a basis for the vector space of matrices with 2 rows and 2 columns and real entries, then I can use that basis almost like it's a dictionary to translate over from the world of matrices into the world of vectors that we can do linear algebra with. So how do we do that? We first pick a basis. And so an example of a basis for the vector space of matrices that are 2 by 2 are these 4 matrices. You should convince yourself that every matrix I can write down that's 2 by 2 that has real entries, I can write it as a linear combination of those 4 things, and that each of those 4 things is linearly independent of the other 3. So that is an example of a basis for this space. So how do we use a basis to translate between the contextual world and the decontextualized coordinate vector? Well, we just have to figure out how this matrix, in particular, can be expressed as a linear combination of those basis matrices, if you like. And we happen to have chosen these basis matrices in a way that makes that pretty straightforward to do. 6, -4, -3, 5 can be written just as 6 times my first matrix plus -4 times my second matrix plus -3 times my third matrix plus 5 times my fourth matrix. In other words, those entries of the matrix are exactly the coordinates, the coefficients of the linear combination of my basis elements that gives me the matrix that I'm interested in. And so I can take these coordinates and package those coordinates together into a vector in 4-dimensional space, because each one of those coordinates is just going to be a real number. I can package those coordinates as the entries of a 4-dimensional vector. And that coordinate vector in the plain vanilla vector space, which is 4-dimensional real space, R4, that coordinate vector is going to act, walk, talk, quack, everything just like this matrix. So these are 2 different names for the same thing. But it's a bit like we're sort of, taking off this matrix's contextual clothes and just looking at the vector that is underneath it, that sort of forms its identity as a member of the vector space R4, rather than as a member of a space of matrices that might have other contextual properties that in other circumstances we might be interested in. So if it's a basis that lets us translate between these 2 worlds, then presumably that means that if we pick a different basis, we might get a different translation. We might translate this matrix, instead of from English into French, we might translate from English into Portuguese instead, right? The same English word, the same idea, just expressed in different languages in different ways. For example, if I took the second and the fourth matrix that are in my basis and I just flip-flop the 2 of them, I'm going to get a different basis in principle, right? And that means I'm going to get different coordinates at the end of the day. But we shouldn't let that dissuade us, right? That we're still talking about the same matrix at the end of the day, even if the coordinates that we use to express it might be a little bit different. So this choice of basis is a choice on which all of our coordinate vector choices and everything that we do with those coordinate vectors might, in principle, depend. And we move into the next chapter and look at algebraic properties of linear transformations. That choice that we make right here is super important. This is the choice, this is the sort of translation process that is super duper powerful, right? Because it lets us express anything in any kind of vector space as a coordinate vector. But we have to know what choice that we've made here in the middle. Because if you just come up to me on the street and you hand me a coordinate vector, I'm not going to necessarily know how to relate that coordinate vector back to something that's contextual, back to something that's meaningful, unless you also tell me what is the basis on which I have defined my coordinates. And if it works for matrices, it's going to work for polynomials as well. So if I have this polynomial, 3x squared minus 4x plus 1, and I choose a basis for my vector space of polynomials of degree at most 2, right? And an example of a basis for that space would be the three functions e1 of x is equal to x squared, e2 of x is equal to x, e3 of x is equal to 1. Those are kind of the basic polynomial functions of degrees 2, 1, and 0, respectively. And they're chosen in such a way that makes it pretty quick for us to see how this particular polynomial can be written as a linear combination of the ones in that basis. The coefficients of that linear combination are just the coefficients of the relevant order terms in my polynomial. So 3, negative 4, and 1. That's how many x squareds, how many x's, and how many 1's that it takes to make my polynomial in question. And so a coordinate vector that we could use to represent this polynomial as a member of a three-dimensional ordinary plain vanilla Euclidean space, R3, would just be the vector that has the components 3, negative 4, and 1, just taken out of the expression of that polynomial with respect to the basis that we chose. So this is the whole idea, that as soon as we can translate from a rich, sort of meaningful type of vector into a coordinate vector, then we have all the tools of linear algebra at our fingertips to be able to answer interesting questions about contextual things by translating them into questions about boring decontextual things. And so we answer the questions over here because we have the tools to answer them, and then we can just translate those answers back into the context that we were interested in the first place. In our next video, we're going to see an example of what it would look like to ask whether a set of polynomials, for example, so context, is linearly independent. It's the kind of question we know how to answer over there, so we just need to figure out how to translate between these two worlds, take my question about polynomials, translate it into a question about vectors, answer it over there, and then translate that back into a question about polynomials.